Okay, last video before the midterm. This is about the central limit theorem and the distribution of sums. This is a long video and it's got some very big ideas, so make sure you're ready for it. The normal distribution is not just everywhere in nature, it also has a very unique property that it adds up. So if you add two normal distributions together, then the resulting distribution is still normal. That's actually very unusual. For example, if you take two uniform distributions and add them together, you get a triangular distribution. And most distributions behave like this. If you add two of the same distributions together, then the result will be some different distribution, but not the normal. The sum of normals is still normal. Here's how they add together. Let's say I have a normal distribution with a mean of 2 and a variance of 9, and another one that has a mean of 3 and a variance of 16. Then the distribution of their sum is normal, and you just add the two means and variances together. It's that simple. Just keep in mind that we can add the variances but not the SDs. We can take this one step further. Let's define S as a linear combination of x and y, where x and y have a normal distribution with their own mean and variance, and a, b, and c are constants. Then the distribution of S will be normal with this mean and variance. And this is just like the formula that we learned a couple of weeks ago. Notice that if A and B are both 1 and C is equal to 0, then we have the regular sum of two normal distributions like we had at the beginning of this slide that you see above. Here are some normally distributed variables that I want you to memorize for now because we're going to use them for about 4 or 5 questions. They represent rainfall, and J is July, A is August, and S is September. So the first question is about the total rainfall for all 3 months. And we need to find the probability that the total is greater than 225. So I need to figure out the distribution of J plus A plus S. Now, since they're all normal, the distribution of the sum is going to be normal as well. And I can just add the means to get 240 and add the variances to get 769. Now we can subtract the mean and divide by the SD on both sides of the inequality. Remember that the SD is the square root of the variance. This creates Z on the left side, and Z is greater than negative 0.54. Go to your Z table and you'll find that the area is 0.7054. So this is the probability that total rainfall will exceed 225. Next, we're going to ignore September and look only at August and July. We want the probability that July is greater than August. Now, a statement like this isn't going to work. We need all the variables on one side and a number on the other side. So I'm going to move A over to the other side of the inequality to get this. Now we need to figure out the distribution of J minus A, so let's look at that. J minus A is 1 times J plus negative 1 times A. So we have coefficients of 1 and negative 1. The result will be normal, and we just need to plug in the means and variances of A and J to figure it out. When we plug in the means, we get a result of minus 10. But remember that when we plug in the variances, the coefficients get squared. So we actually end up adding the variances to get 369. Now we create Z by subtracting the mean and dividing by the SD. We get Z is greater than 0.52. which according to the Z table has an area of 0.3015. So that is the probability that it rains more in July than in August. Okay, in this question, we want the probability that S is greater than J plus A. That September exceeds the combined rainfall of July and August. This time, I'm going to move J and A over to the other side to get this. Now we need to find the distribution of S minus J minus A. The result will be normal, and we just need to find its mean and variance. When we plug in the means, we get a result of negative 40. When we plug in the variances, we square the coefficients, and we end up with a result of 769. Now we can create Z by subtracting the mean and dividing by the SD. We get Z greater than 1.44. Look it up on the Z table, and you'll get an area of 0.0749. So this is the probability that the rainfall in September exceeds the combined total of July and August. Okay, this question is about average rainfall, which seems different, but it's still just a linear combination of the variables. We want the probability that average rainfall for the 3 months is less than 85. Now let's rewrite it as 1/3 J plus 1/3 A plus 1/3 S. It's the same thing. But now we can see that the coefficients are in front of each variable. We're going to find the distribution of this expression. And since these variables are all normal, the result will be normal as well. We just have to figure out its mean and variance. When we plug in the means, we get a result of 80, which makes good sense because that's the average of the 3 means. But when we plug in the variances, all the coefficients are squared and we get a result of 85.44. Now we create Z by subtracting the mean and dividing by the SD. And I've skipped a step here because rewriting this entire expression is kind of tedious. But this 85, remember, that came from the problem. It's in the previous slide. Okay, so Z is less than 0.54, which is an area of 0.7054. So this is the probability that the average rainfall is less than 85. Okay, now we want the probability that the average rainfall of all 3 months is greater than the rainfall of August. So I'm really asking for this. This time I'm going to move the A over to the other side and then rewrite the average like I did in the previous example and simplify to get this. What I have to do now is figure out the distribution of this expression. And since these are all normal, the result will be normal. We just have to figure out its mean and variance. When we plug in the means, we get a result of 5. And when we plug in the variances, all the coefficients get squared, and we get a result of 160.44. Now we create Z by subtracting the mean and dividing by the SD. Remember, the 0 here came from the previous slide. That was on the right side of the inequality before I began to find the mean and variance. Anyway, we get Z greater than negative 0.39, which has an area of 0.6517. So this is the probability that the average of all 3 months is bigger than August by itself. That's a pretty difficult example, but if you stick to the formulas, you'll get there in the end. But there's more. The title of the video is the central limit theorem, and that's what I'm going to talk about next. This theorem applies if you have many random variables that all have the same distribution, which may or may not be normal. If the variables are all independent, then the distribution of their sum is approximately normal. And the more variables you have, the closer the approximation will be. This result is called the central limit theorem, and it's a pretty amazing thing. This explains why the normal distribution is so important to us. You could, for example, add up many uniform distributions, and the distribution of their sum will be approximately normal. Or you could add up many coin flips, and the distribution of their sum will be approximately normal. It doesn't matter what kind of variables you begin with, as long as they're independent and identically distributed, then the distribution of their sum will be approximately normal. Here's a more formal definition. Let's say we have n variables, and since they all have the same distribution, it makes some sense to use the same letter for all of them. And I'm going to call them all x. So x1 is the first variable, x2 is the second variable, and so on up to n. Since they all have the same distribution, they all have the same mean, mu, and variance, sigma squared. Then the sum is approximately normal with this mean and variance. And their average is also approximately normal with this mean and variance. All right, let's use this in an example. We're going to roll 100 dice, and we want the probability that the sum is at least 380. Before I go on, we need some facts about one die roll that we learned before. This is the mean and variance of one die roll. If we add up 100 die rolls, then the distribution of their sum is approximately normal with this mean and variance. I used the theorem from the previous slide, so the mean is n times the mean of one die roll, and the variance is n times the variance of one die roll, where n is 100. Before we go any further, we need to realize that die rolls are discrete, but the normal distribution is continuous, so we should apply the continuity correction. Since the question asks for the probability of a sum greater than or equal to 380, we should change that to 379.5 for the continuous scale. Now we can create z by subtracting the mean and dividing by the SD. And when we look this up in the z table, we'll see that the area is approximately 4%. And so that is the probability that the sum of 100 die rolls is at least 380. Okay, in this last example, we still are going to roll 100 dice, but this time I want the probability that the average is less than 3.65. So here again is the mean and variance of one die roll. Then the distribution of the average of 100 die rolls has this mean and variance. Remember that the theorem stated that the mean of the average is the same as the mean of one die roll, and that the variance of the average is equal to the variance of one die roll divided by n, so divided by 100. Okay, moving on, the average is continuous, not discrete, so we don't need the continuity correction. So we create z by subtracting the mean and dividing by the SD, and we get z less than 0.88. The z table says this area is about 81%. So this is the probability that the average of 100 die rolls is less than 3.65. Okay, there were some pretty big ideas in this video, and we're going to do a lot of questions about this in class. Going forward, we're going to spend a lot of time and energy talking about averages especially, so it's important to understand their distribution. Okay, you've got 3 questions to do. Good luck with that, and I'll see you in class.